Hi, this is part 2 of my video on taking you through the formulas for finance that are on the QCAA General Maths formula sheet. So this one I'm focusing on the annuity formulas. So first of all, I want to just explain a little bit about what an annuity is and how you would recognize the situation. So basically an annuity is when we have a regular payment involved. So we can either be, for example, taking out a loan and then making regular repayments for it, or you might see a question that's about purchasing an annuity and receiving irregular payments. So for example, let's say you won the lotto and you had this big lump sum of money. You could invest in an annuity and then it would like drip feed that money back to you in a regular payment whilst the money was earning interest at the same time. Now the other situation is if you're saving up for something, so you might be making a regular payment into an investment account and then you want to work out how much you've got at the end of that time. So both of those situations are annuities, and I've got them demonstrated on what I call like a timeline. So the first situation, what you want to think about is we've got that big lump sum of money at the beginning and the regular payments coming out, and these payments, if they are all brought back in time using compound interest, they would all be equivalent to this amount at the beginning. So because these payments have to come back in time to equal the A, that means we've got the formula with the negative n in the formula. If, on the other hand, we've got all the payments going in and our big lump sum of money is at the end of that time period, then all these monthly or regular payments, not necessarily months, when they're taken forward in time using the compound interest, they'll be equivalent to this big lump sum of money here at the end. So they're going forward in time, so we need the positive n formula. Now both of these can also be modelled with recurrence relations. So this one here, where we're adding in the payment and accumulating those payments over time, that's this one here with the plus d in it. But when we have this situation where we've got that initial investment amount and we're either, or if it's the loan and we're making monthly repayments and our balance is reducing, then it's this one here. Okay, so even though the formula sheet, it says recurrence relation for reducing balance loan, we can use it for the situation where you purchase an annuity and receive a regular repayment, because your big lump sum of money here is at the beginning and we're taking those payments out over time. So now let's look at some example questions and see if we can work out which formula we're using in each case. So here, this time, we've got a loan of $500,000 taken out to purchase a home, and interest is paid at 4.5% per annum, compounding monthly. The loan's repaid after 20 years, and what will be the monthly repayment? So first of all, if we think of that on the timeline like I did on the previous slide, so thinking about our big lump sum of money is here at the beginning. The bank is going to give you that $500,000, and then you're going to make regular monthly payments in this case to repay that over time. And then by the end of the 20 years, so our final n, remember our periods here are months, so 20 years is equal to 20 times 12, which is 240 months. So we're making these payments over time, every month, same payment, and then by the end of this time, the loan is paid off. Now, if we want to work out what those monthly repayments are, think about, we're looking at the big picture of the overall time that we've got this loan going on. So that's where we're going to use, looking back at our formulas here, we're going to use annuity formula down here because we're looking at the overall big picture and we need this formula here. It's only when we focus in on just a few months at a time or whatever that we're going to use our recurrence relations. So let's popping our formula in, then we just have to put everything in the formula. Now our A, that's our 500,000. The M's what we want to know, so that's going to just stay there. Now our interest rate, remember your I has to go in as a decimal, but also it has to match the compounding period. So that's going to go in as 0.045 over 12. And our final N is 240. So when we simplify that, we're going to have M times 158.06543,681, and then dividing that over is going to give us an M value 3,163.2468811. Obviously it's dollars and cents, so we'll round that off to 2 decimal places, $3,163.25. Okay, let's have a look at another example. So this time we've got a situation where we want to save up $25,000. We're going to make a regular payment into an account that's paying interest at 2.3% per annum. So if we do the timeline again, we've got nothing at the start. We want to have 25,000 at the end. That's what we're saving up for. Now we're doing it for 5 years, and 5 times 12 equals 60. So that's our N. And we're making a regular payment the same amount, so that's going to go in each month. So because we're going forward in time, remember now the payments are all going forward to save up for this lump sum, so we need the formula with the positive N. So putting that in, then we just have to put all our bits in there. So our 25,000 is our A. Once again, the interest has to be as a decimal and then per compounding period, which in this case is months. And then our N is 60. So when we simplify that and solve for our M, we're going to get M is equal to $393,057. Now we know that. We want to find out how much will be saved after 6 months. So notice this time we're just zooming in on a little portion of our timeline. So this is when the recurrence formula is going to be useful. So the recurrence formula, remember that we use in with the same one here when our payments are going forward, is the one with the plus D in it. So we're going to have AN plus 1 equals RAN plus D. So just making a note of what our bits are, we need to remember that A naught, in this case it's 0 because we start off with nothing. Our R, remember, is 1 plus I, so that's 1 plus 0.023 over 12, and when we put that in the calculator, 1.001916 recurring. So we want to try and keep as much detail of that number as we can for accuracy. And our D, that's our regular payment. So in this case, it's the same as our M up here. So it's $393.57. So we want to know how much is saved after 6 months. So for example, we have to go through each term. So term A1, the balance at the end of 1 month, is going to be 1.001916 recurring times A0, which is 0, plus 393.57, which is going to be 393.57. Then our A2, we'd have 1.001916 recurring times that previous balance, plus another payment. So that comes to $787.91. Now, if you keep doing this, remember to set your calculator up so that you can calculate this easily and do a repetitive calculation without having to retype everything for every calculation. We're going to get A3 is $1,182.99. We'd keep going, we'd get A4, A5, and then our A6 is the one we want. If we keep processing that recursive formula, we're going to end up with $2,372.78. Okay, let's have a look at another example. So this time we've got an annuity is purchased for $230,000, interest paid at 4.7% per annum, and a monthly payment of $1,250 is received. So once again, I'll just visualize what's happening on a timeline. So this time we don't know how long this is going for now, so I'll just put N up there. So we've purchased an annuity, so that means our big lump sum of money is at the beginning. We've put that into the investment, and then they're going to keep paying that back to us in regular payments of $1,250. So if we want to know what the balance is after the third payment, once again, we're just honing in on the first few months of this. So that's the recurrence formula. Now remember, when we've got our situation with the big lump sum at the beginning, and all our payments are then coming out after that, it's this recurrence formula here with the minus R. So then just thinking about what our little bits are. So A0 in this case is 230,000. The R, as always, is 1 plus I. So in this case, it's 1 plus 0.047 over 12. And when we simplify that, we get 1.003916 recurring. And our capital R, that's our regular payment of $1,250. Now when you put this in, we'd get the first one is just going to be 1.003916 recurring times our A0, which is 230,000, and then take off that regular payment, and that comes to $229,650.83. Then we just have to keep putting that in. That goes in as our new balance there, so it'll be 1.003916 times the 229,650.83 minus that 1,250, and that's coming out to 229,330 cents. Now if you repeat that process, we just want to know the balance after the third payment. So that's our A3, which I won't write all that out again. I think you get the idea of what we'd put in, and that would calculate to $228,948.39. Okay, so now what we need to know is how many of these payments are we going to receive? It's obviously not going to go on forever, because that 230,000, unless of course we were earning more interest than we were actually taking out in a payment, then that it could literally last forever. But let's assume that for the moment that we're taking out more than we're earning in interest. So now we're looking at the big picture. When we want to know what our N is, how many of these payments, we're looking at the overall situation. So going back to our formula sheet, we've got our lump sum of money here with all these regular payments, and we want to know how many. So it's the formula with the negative N in it that we're going to be using. We'll put in what we know. Our A is 230,000. Our M is 1,250. And we've got here our I is the same as the I that we used up here. Well, I could put in the 1 plus I, but I'm just going to put it in back in original form there, and we've got the negative N, and the I here again is that. Now, we could rearrange this and solve it algebraically, but if you didn't feel up to that, we can use a guess and check process would be okay as well. So what I would suggest doing is setting up like a little table where we're going to do the guessing and the checking. So we want to have our N is what we'll take a guess at what we think might be, and then we're going to calculate this whole right hand side, and we're looking for it to get close to this, close as we can without going over to this 230,000. What you want to remember as well is that your N is in months. So we can think years, but we need to turn it into months. So what I was thinking as a good place to maybe start is to think, what if it was 20 years? Now 20 times 12 is 240. So that 240 months. And when we put that in the right hand side, in all of this bit here, it comes to 194,251.37. So that's telling us that we can go a little bit higher. So perhaps if we tried 25 years, that would be an N of 300. Now that calculates to $220,363.23. Says we're not quite up to that 230,000 yet, so we can go a bit higher. So may as well just jump up and try 30 years. So that's an N of 360, and that calculates to $241,015.98. So you can see we've gone over our 230,000 now. So 30 years is too long. We're not going to get that many payments. So I'll take it back a bit to 27 years, which is an N of 324 months. Now when I put that in, that calculates to $229,209.50. So we may get another payment, we're not sure. So I'll take it up to, I'll just talk in the months now, and I'll go 326. Now that calculates to $229,909.91. So we're really close now. So just to check that we can't sneak another payment in there, I'll go to 327. And when I put that in the calculator, for that whole right-hand side, comes out to $230,258.06. So that tells me that I am not going to get that extra payment out. I am only going to get 326 full payments of $1,250. And the last payment just won't be that much. It'll just be a bit smaller than that. So we could just sum up and say, therefore, 326 payments of $1,250 will be received. So there's an overview of the annuities and a few different examples showing some different scenarios. Keep a lookout. I'm going to do another video which goes through a more complex annuity situation. So hope that's helped. Look forward to helping you with further videos.